So I wanted to make a video here on the geometry of curves. And so the geometry of curves, there's basically those things we can calculate for a path, and those things which we can calculate that are intrinsic to the curve somehow. They describe the shape of the curve in some sense. And so it turns out for curves in 3 dimensions, essentially the geometry of the curve is described by arc length, and then by curvature and by torsion. And we can calculate these using what are called the tangent, normal, and binormal vectors. These together form the so-called Frenese apparatus of the curve, and I'm going to describe in the next tens of minutes how we can calculate those things and understand them. So let's get started. Geometry of curves. So to start with, just think about a curve in space, right? And here it goes, round and round it goes, where it stops. Well, it stops right there. But so I'm just using T0 and T1 as the T0 to T1 as the domain of the curve. I mean, it could go to infinity. It could start at minus infinity, but then you got to decide where to start the integral. In any event, if you integrate the speed over the time period T0 to T, that gives us the arc length that's been traveled up to that point. And we can understand why that is if we just look at some little pictures. I mean, here's a motivation. I mean, that is a definition, but here's a motivation for the definition. If you look at this like little bit of arc length, we could approximate it by the velocity times change in time. And as delta t goes to 0, this purple line and this blue curve, they get closer and closer together. And so like to calculate the distance from here to here, I can use the 3-dimensional distance formula, delta x, delta y, delta z squared, square rooted. But if you use your imagination, you could also like divide and multiply by delta t squared and see why we could describe that in terms of something having to do with the speed of the curve, right? So as delta t goes to 0, we find that delta s is something like the speed times delta t, which means that our definition is quite reasonable. Let's see here. All right, so again, here's yet another notation, arc length at time t, integrate from the initial time all the way out to time t, and this is the length of the velocity, which is the square root of, so sometimes, by the way, this is sometimes that square root you could rewrite as the square root of, and I like this notation, x dot squared plus y dot squared plus z dot squared. That's the physics notation. This would be another formula for speed, by the way. X dot y dot z dot are the velocities. So in any event, fundamental observation here is that when we differentiate the arc length function with respect to time, the fundamental theorem of calculus says that when we differentiate an integral variable bounds, so this integral is done over tau because I can't use t in the same sense as here. So tau is just like a dummy variable of integration. You could put u and u here just the same, it wouldn't be different. But in any event, when we differentiate the integral with the variable bound, we just plug in that time into the integrand, which gives me d gamma dt, which, well, that's the velocity. I mean, this is nothing more than the magnitude of the velocity of the curve at time t, which is to say that the change in arc length with respect to time is the magnitude of the velocity, which of course we also call the speed. So there you go. The instantaneous change in arc length is in fact the speed. That's a derivation of that fact. So this is a slogan I use to set up integrals and things. I'll use this again through anytime we're thinking about how to set up an integral. I usually try to think about how to set up an integral for a curve with respect to arc length, and how I understand the infinitesimal arc length is always through multiplying the speed by dt, where t is the parameter of the curve. So this is kind of like a useful mnemonic, if you will, a memory device for remembering how to set up integrals that involve ds later. But anyway, so I haven't said anything new there. I'm just that's the formula for the infinitesimal arc length. We integrate that in order to get the actual arc length. Okay, so it's time for a summary about things we know of. We can notice here. Number one, arc length is the integral of a positive quantity, right? Well, a non-negative quantity. I mean, I suppose that could be 0. So certainly the arc length is non-negative. That's one thing. We can also observe that the arc length is an increasing function, right? Because, well, how do I know that? I know that ds dt is what? It's the speed, right? Which, of course, is the magnitude of the velocity, which is, by the way, greater than or equal to 0. So if you have a function whose derivative is greater than or equal to 0 everywhere, that means it's an increasing function, and if the velocity is non-zero, then it's strictly increasing, meaning that it can't level out even. All right. Now, for speed rather non-zero, for some interval, we can also say that there exists an inverse function for arc length. In other words, we can find S inverse, which goes from 0 arc length to the total arc length S1 back to the range of the time parameters. This makes sense if you think about a function which is everywhere increasing. It's going to pass the horizontal line test, so you can invert it. The function's 1-to-1, so we can find an inverse. But in any event, any curve permitting a nonstop differentiable parameterization can be parameterized by arc length. And I'm going to use gamma tilde to indicate that special choice, which, by the way, is unique up to our choice of starting point. In contrast, there are many paths which cover a curve, right? We could choose many different parameterizations of a curve, but once we pick a starting point, there exists a unique, that's what this means, there exists a unique arc length parameterization of the curve, all right? So I know that this bullet list, I mean, this is not, points 1 and 2 I think are not too surprising. Point 3 might be a little bit surprising. Point 4 is probably not going to be understandable until you see the following example. So let's look at an example where I actually do explicitly construct the gamma tilde. All right. So, well, actually, I think to start with here, I'm just calculating arc length. This guy, I don't think I can actually solve the arc length in terms of time. Let's see here. So here's my curve. Oh, the parameterization of the curve, right? Technically a path. And so I calculate the derivative, which gives me the velocity, right? The magnitude of the velocity is the speed, right? Now, you could also say that this is equal to s dot if you liked. S dot is ds dt is equal to the speed, all right? And of course, the thing above is exactly the velocity, right? At time t. Sometimes I omit the of t, but anyway, moving on here. And then, so to calculate the magnitude of this guy, some really cool stuff happens when you look at that squared plus that squared plus that squared. You end up with this, you end up with picking up like cosine squareds and sine squareds and t squared sine squareds and t squared cosine squareds. And then the middle terms, you get yourself a minus and a plus too. Those guys cancel. And so it all collapses down to something reasonably simple, the square root of 1 plus 5t squared. So the infinitesimal change in the arc length is the square root of 1 plus 5t squared. And I just said something I probably should write out. I said the infinitesimal change in arc length now is product of speed and dt. Okay, anyway, and then we integrate that to get the actual arc length, but that's all we can do. Like this integral, I think it's a storied integral. I believe this is an elliptical integral, and it has an answer in terms of elliptic functions, but that's just really name calling for saying the function's defined by the integral. I mean, I don't think this is something I might be able to do in close, I don't know, that might be able to get like an inverse hyperbolic something to get that one, possibly, I'm not sure. But anyway, a lot of times I like to ask a question that has the following instructions. Find arc length in terms of, and I guess I should probably a little bit more English here, of an integral. And so there it is. That's the arc length up to an integral. And so if I say that, and then I usually will put in bold, do not attempt the integral. You know, if I write that on a test, you better not attempt the integral, because there's a reason I wrote do not attempt the integral. It's either because you don't have time on the test, or it's because the integral can't be solved in elementary terms. All right. In example 2, here's one. This is a plane curve. I just did two-dimensional, right? So t squared t cubed, find the arc length, find the velocity, find the speed, integrate the speed from 1 to t. Notice my dummy variable of integration is tau. Again, you could just as well have written, by the way, I'll just write it here. It would be no different logically to write the square root of 4u squared plus 9u to the 4th du. The thing is, I can't use t in the integration variable because it has a specific and other meaning, because it has to appear in the bound, because we're doing s of t, so this t has to be that t. And I can't use t again in the integration because that would be illogical. But I'm sure some engineers do it and get away with it. But anyway, we'll try to be better than that. And so, by the way, I actually think I could straight up do that integral, because if you look at it, you can factor an x out, and there's the antiderivative of this, and you could do it, but, you know. Yeah. All right. So I still haven't showed you how to find the unit speed parameterization of a curve just yet. Let's look at, maybe I'll do that next year. So just to reiterate, given a curve parameterized by time, we can calculate the arc length. That gives us s of t equals to formula. Then we could solve that formula for t, right? Then we could write gamma tilde of s is the original path evaluated as g of s. This is basically the algorithm for, this is like how to construct the arc length parameterization. All right, so gamma tilde is, again, called the unit speed parameterization or arc length parameterization of the curve. And let me actually, so I'm going to make good on this algorithm in the case of a helix. All right, let's see here. So initially the formula for a helix with radius r and slope m is something like this. X equals to r cosine t, y equals to r sine t, z equals to mt. I suppose to be, I mean, we could say that, you know, t is a real number. I'll say t is an element of 0 to infinity, just to keep it a little bit easier to think about. So a picture of this is, it starts at time 0. Where we put in 0, we get r 0, 0. So it like starts here, right? And then this curve, this kind of, wee. Here, I'll just go through my other thing. Wee. Roughly speaking, and it's wrapping around the z-axis. This is a helix. Now, so the velocity is that. The length of the velocity, cool thing, sine squared plus cosine squared is 1. So the length of the velocity, in other words, the speed, is you know, s dot if you like. I use the notation s dot a lot in the type notes that I provided for this material. Anyway, the speed is actually the square root of r squared plus m squared. And when I calculate the integral of the speed with respect to time, I get time times that number. And, well, that's pretty nice, because I can actually take this formula, right, and I can solve that for t just by dividing by the constant. So I get the time is equal to the arc length divided by the square root of r squared plus m squared. My cautionary red bubble is that, hey, hold on a second right there. In many examples, this step is not actually possible. You know, it could be that you can't actually solve for a formula in S, like that first example where we had the elliptic integral, or the second one. You know, maybe you don't actually have a formula for S, so you can't do it. It could be that the formula for s has t in a complicated way, like s could be equal to t cubed plus t squared, plus 3 or something like that, and you'd have to like somehow solve for t. Well, we probably can't do that for a lot of formulas. Yet it's theoretically possible because the arc length is an increasing function. So just because it's theoretically possible doesn't mean that it's practically implementable with closed form algebra. Anyway, here it is for this curve. So the helix, the unit speed parameterization of the helix, I take t and put in place the corresponding formula for s, which in this case is s over the square root of r squared plus m squared, and plug it in. There you go. This is the unit speed, quote unquote, unit speed or arc length parameterization of the helix. So I probably have a homework question like that, find the unit speed parameterization of a given curve. And here's a calculation which shows you why we call it unit speed. When we calculate the derivative with respect to s of this function right here, I'll introduce alpha as 1 over root r squared plus m squared to clean things up. And when I do that, I work through the calculus and I get that the magnitude of the velocity in this, with using s as the parameter, the magnitude of the velocity is just 1. In other words, it has a unit speed. So, I'm going kind of fast through that. It might take you like 2 or 3 minutes to work through that calculus. I'm going to go on though, okay? So summary. Given a smooth curve, C, and a point r of t naught, and a path which covers that curve, we can find a unique arc length function such that gamma tilde, going from 0 to the total arc length, provides a unit speed parameterization. And I'm going to use this gamma tilde to formulate the geometry of C, and the reason for that is just that I'm introducing everything via arc length parameters since it's unique. And I will give you formulas for these things in terms of time a little bit later, maybe about 10 minutes. Maybe less, I don't know. We'll see. Anyway, here's a picture. So if you have a curve, which is the gray thing, you can attach a vector along each point in the curve, and that's called a vector field along the curve. There are 3 natural vector fields to attach along a curve that we're studying. We can attach a vector field which is the tangent vector, like attach the tangent vector at each point. We can attach the normal vector, which points towards like the center of a circle. If you could imagine fitting a circle into here, the normal vector sort of, here I'll do it done. Let me do another one over here. Whee! So like the normal vector, if you can imagine, I think you can imagine fitting a circle into here, right? Like that. There'd be a little circle that fits in there. There'd be a bigger circle that fits in here, so to speak. This is the so-called osculating circle. Osculating is like fancy old English for kissing. So it just kisses the curve. And so like the osculating circle, the normal vector points towards the center of the osculating circle like this. All right. Now I'm not doing it quite right because the normal vectors, these are a unit vector. So like all the n tildes should have length 1. They should all have the same length. My pictures are never quite successful in having all of the n's and the t's and the b's having the same length, but they should, logically, because here's how they're defined. First of all, the unit tangent we define to be gamma tilde prime. Now we know that that has unit length because, remember, the magnitude of the velocity is the speed, and when we parameterize with respect to arc length, essentially, ds dt is what? It's really ds ds, so no surprise, it's 1, right? So unit speed. And tilde, we take the derivative of the unit tangent and divide by the magnitude of that. So basically the unit n tilde is essentially t tilde hat. It's the unit vector in the direction of increasing t tilde. And then to get the binormal, we just take the cross product of the previous two, and that gives us yet another unit vector. Together, t, n, and b form a right-handed triple, like I mentioned in the previous class. Now, just a little flash forward here. I'll come back to this more in a second, in a little bit later. But to get to the time version rather than the arc length version of the unit tangent, we end up having to look at the chain rule. So like the path at time t is equal to the unit the arc length parameterization at s of t, and so if we differentiate that, we get the velocity with respect to time is the velocity with respect to arc length evaluated at the arc length with respect to time times the derivative of the arc length with respect to time, which is to say t tilde of s of t times ds dt. And so to get t of t, we take the velocity and divide by the length of the velocity, which when we parameterize with respect to time, there's no reason to expect that the speed is 1, right? So this actually is more interesting when we're not working with arc length parameterization. But again, I'm going to start with arc length parameterization because logically it means the things we're defining are uniquely defined because, well, there's a unique choice of arc length parameterization for a curve. That's why we start with arc length, is just, to make sure that we're not defining something that depends on the parameterization, because there are many parameterizations for a curve. Okay, so the next 2 pages or so, I'm going to derive what are called the Frenese ray equations. And here you'll actually get to see some of those calculus of curves, calculus of path identities that I wrote down, actually, being used to say something quite non-trivial. So to start with, here are the definitions for t tilde, n tilde, b tilde, right? T tilde was the velocity, well, the unit velocity in this case. I should say it this way. T tilde is a unit vector in the direction of the velocity. N tilde is the derivative of t tilde normalized to length 1, and then b tilde, the binormal, is the cross product of t tilde and n tilde. And we're going to investigate how this Frenese frame, t tilde, n tilde, b tilde, evolves as s changes. So first, let's figure out what the angle is between these vectors. What do you think? So notice that since it's got unit speed, the dot product with itself is 1. But if we differentiate that, that shows us that the derivative of t and t are perpendicular. But notice that the derivative of t is a scalar multiple, n tilde is a scalar multiple of the derivative of t, right? So that implies that t tilde and n tilde are perpendicular. And then, of course, b tilde is going to be perpendicular to both of these because it's a cross product, right? So I get to that down here. But so we can define one thing already. We can say that the curvature, and I wrote a tilde over it because it's curvature as a function of arc length. The curvature is the magnitude of t tilde, the derivative of t tilde. So magnitude of t prime. And so what that means is that the time, the change in t tilde is kappa times n tilde. So this is one of the Frenese ray equations. It says that the change in the tangent vector is the curvature times the normal vector. In other words, this says something, it says that the tangent vector has to, the change in the tangent vector has to go into the direction of the normal vector. And there's a constant which describes that change. We'll look more at pictures of that in a second here. Well, maybe about 10 minutes, but now since b and t and n are perpendicular, we also know that t dot b is equal to 0, right? And so I differentiate that. It gives me t prime dot b plus t dot b prime equal to 0. And so that tells me that t dot b prime is minus b dot t prime. But remember, t prime is kappa n tilde, right? And so, but this is 0 because b dot n tilde is 0, which shows me then, for one thing, that t dot b prime is also 0. In other words, there's no tangent component to the change in the binormal vector. I call that equation Pac-Man for future reference. Likewise, if we differentiate t dot n equal to 0, it shows us that t dot n prime actually works out to, again using this here, so I traded d tilde ds for kappa. There's a minus because I moved it to the other side, and we get minus kappa tilde n tilde dot n tilde, but that's 1. So we've got t tilde dot n prime, let's say, is equal to minus kappa. I'll call that ghost. We'll come back to it in a second here. So it is also helpful to consider. I'm trying to get all my cards on the table here, and then we'll put it together, and we'll have the equations. All right, it's a little bit complicated, but just stick with me here. We'll get to something we can use, and I'll show you how to apply it in just a bit. So since B is t cross n, we have the product rule for cross product, which is the sum of the cross products with the derivatives of the first and then the second, maintaining the order. That's the product rule for the cross product. And so remember, t prime is kappa n, right? So kappa n cross n, well, that's 0. Any vector with itself is 0, cross product, right? And so we're just left with t tilde cross dn tilde ds. So b prime is t cross dn tilde ds. That's okay. Well, there's something to know. And then my goal here is to calculate dp b prime and n prime as simply as possible. So one of the other things I should notice is that we can write like a little circle, just like we write for x, y, z. See, because t and b is also a right-handed triple, it enjoys the same properties as x hat, y hat, z hat. So if I have defined b is t cross n, it follows that's just like saying z is x cross y, right? So z cross x is also y. So I can get from this to also say that n tilde is b cross t, which means I can calculate d and d tilde by differentiating that. So there it is, b prime cross t plus b cross t prime. But I already know, again, from the red equation on the previous page, this guy, that I can replace t prime with kappa n tilde, right? And so remember, b cross n tilde is going opposite the circle, right? So that's minus t. That's why I get this minus t here. So b cross n minus t, and then I still got the b prime. Oh, this is a lot to say. B prime cross t tilde there. All right, great. So then what? So then, I would point out that since these are unit vectors, it also follows that they are perpendicular to their derivatives, right? B is perpendicular to b prime, n is perpendicular to n prime. And so I can use that. N prime only has, it doesn't have an n component, right? So, like, remember, any vector we can write as any. So let me just show you what the logic is here behind these equations down here. So, like, in the same way that we can write any vector, let me give it. I'll use a. I don't think we've used a for anything else here. So of course we could write a dot x hat plus b. Oh, good grief. A dot y hat plus a dot z hat, right? We can expand the vector like that. Well, t, n, and b are just the same. So we can take any vector at a point and we can expand it as t dot a, t plus n dot a, n plus b dot a, b. I guess I should have tildes at this point on these guys. Tilde. Because they form a right-handed triple, I can expand any vector in terms of components of these three fundamental vectors. And so I'm doing that for the particular case that a is equal to n prime. But the thing is, I know that n prime has no component in the n direction, so I only have to think about the t tilde and b tilde directions. And so t tilde dot n prime on the previous page, the ghost equation, that was minus kappa. And then I've got b tilde dot n prime b tilde. And on the other hand, for the b prime, I also know that this component's 0 because of the Pac-Man equation from the last page. And so I've got b prime is equal to n dot b prime n tilde. In other words, I have shown that there is only a n tilde component to the change in b. And that leads us to make yet another definition. And so in view of that, we can define the torsion as follows, because we've just learned that the change in the binormal is only in the normal direction. And so it is logical, so I'm just collecting the calculations I just said once more. So we've got this n prime is minus kappa tilde, minus kappa t tilde, and then we've got b dot n prime b, and we also have b prime is n dot b prime n. And so we define the torsion to be minus that number, whatever that is. So the torsion is minus n dot b tilde ds. That is the torsion at gamma tilde of s. So there's another one of the Frenese ray equations. One more to go. Here it is. So because we have this right here, n prime is minus kappa t tilde b db cross t dbs b prime cross t, but we just said that b prime is just minus tau n tilde. So, and then n cross t is actually minus b. Minus minus gives me a plus, and there you go. N prime is minus kappa t tilde plus tau tilde b tilde. In other words, the rate of change of the normal with respect to arc length is proportional to minus the curvature in the tangential direction plus the torsion in the binormal direction. And these, my friends, are the famed Frenese ray equations discovered by Frenese ray sometime in the mid-19th century. I believe mid-19th century. It'd be before that, actually. Maybe 1840s, I forget. But these are very interesting equations because they essentially describe how the curve is shaped in terms of how this tangent, normal, and binormal are changing along the curve. Right, through these two functions, curvature and torsion. So often we don't want to work with arc length, right? And so the basic thing is that to take a vector field that's the change with respect to arc length, and we want to write it in terms of the change with respect to time, basically the long story short of it is we can just multiply by ds dt. So dv tilde ds times ds dt is essentially dv dt. So if I take the Frenese ray equations and I multiply them by speed, I get the Frenese ray equations for non-unit speed curves. So here's what we actually tend to use to calculate, because honestly, folks, I don't like to parameterize with respect to arc length. Parameterizing with respect to arc length is kind of a drag, so it's more fun to use these equations. There's just an extra speed in each one of these, all right? And that also means we define curvature and torsion for a non-unit speed curve. There's also a speed factor, so like curvature is 1 over the speed times the magnitude of dt dt, and the torsion is minus 1 over v, derivative of the binormal dot n, and the speed of the curve is the magnitude of the velocity. That doesn't have to be 1 for an arbitrary curve. To be clear here, the b and the n are the binormal and normal defined with respect to time. I guess I should have written that here, but so like t of t is it's really just the it's really just v hat. What it is it's the velocity vector divided by the length of the velocity vector. That's the unit tangent. For a unit speed curve, that speed factor was automatically 0, right? But I mean, fine, as long as we're engaging in this cavalcade of notation. This is v divided by s dot. So that's the unit tangent when we're not working with arc length parameterized curve. The unit normal is still just t prime of t divided by the length of t prime of t. Okay, so anyway, and the binormal as a function of time is still just t cross n. So it's a little bit different, but not too much different to calculate TNB for the time. Basically, you just have to remember to rescale your unit tangent by dividing by the speed. Okay, so an example. Let's actually calculate this stuff for a circle. Here's a parameterization of a circle. I'll calculate the tangent vector field. So I differentiate, I find the length of the velocity vector, which is the speed, it works out to r. I then divide by r to calculate the unit velocity vector field, which is called the tangent vector field, and that's minus sine cosine 0. So there you go. Next up, we'll calculate the normal. The normal field is given by t prime over the length of t prime. In this case, t prime is just minus cosine minus sine 0. That is actually a unit vector, so when we divide by that, it's just dividing by 1. It's kind of silly. It just so happens that n is equal to t prime in this case. So there it is. And then the binormal, we take the cross product of t and n. As usual, we get something kind of neat, sine squared plus cosine squared from the z, minus minus, and then minus from the formula, and a minus from that. So we get sine squared plus cosine squared. So the unit, the binormal, is actually just z hat in this case. And the curvature we can calculate is 1 over the speed times the magnitude of dt dt. Remember, the magnitude of dt dt was just 1, and the speed was r here. So the curvature is 1 over the radius of the circle. And that actually is generally true. So like, in the sense that if you had a curve that's more interesting like this, the curvature is not the same at all points on that curve. But what is true is that if you look at the osculating circle, like the radius of that oscillating circle is r, then that's equal to 1 over the curvature at that point on the curve. So like the curvature in this part of the curve, like over here, roughly speaking, I can't draw it. It's bigger, right? I just try not to get into that. But so the curvature is it's going to be smaller over here because the radius of the oscillating circle is bigger. Whereas over here the curvature is greater because the radius of the oscillating circle is smaller. I have more to say about how curvature can be thought of geometrically, but that's in my notes, so I'll come back to that at the end. Now the torsion here is 0 because when we differentiate b, we get 0, right? So 0 dot n is 0, so the torsion is 0. In fact, there's a theorem that if we have a curve with nice t and b, then it's a planar curve, which means it lies in some plane if and only if the torsion is identically 0 on the curve. Here's a sketch of the proof of that. Basically, it's that dp dt is minus tau vn, right? And the normal's not 0, the speed's not 0. So in order for dB dt to be 0, it must be the case that the torsion's 0. However, if the torsion's 0, that means that dB dt is equal to 0, which means that we can argue that the binormal is a constant, and that will serve as the normal vector for the plane in which the curve lies. Now, actually proving that is a little bit involved, okay? But it's true. The actual solution to this, I think, is, for me, it's like 2 or 3 pages long. So this is a sketch of a proof. It's not quite a complete proof, right? On the other hand, if the curve is planar, then we can show that b of t is constant, and hence the torsion 0. But anyway, I'm just warning you that if you're really picky and you want to prove this carefully, for me it takes a while. And that's time we should spend on other things this semester, I think. So, all right. So another example, the helix. So this is, here's the helix with radius r and slope m. So I find the velocity. That tells me the speed, again, is root r squared plus m squared. So the unit tangent, I divide by speed, I get that. I usually use alpha as 1 over root that just to make the formulas look simpler. I'll eventually start doing that when we get down to the binormal. But differentiate to find t prime. All right, and then so this is a trick. If you differentiate something and you find a vector, if you can rewrite the expression so that you've got some factor times some vector, and that vector is clearly a unit vector, then the magnitude of such a thing is just the value of that, right? Because if you have something times a unit vector, the length of that vector is whatever you're scaling the unit vector by. So that must be the magnitude. So the magnitude of t prime is just r over the square root of r squared plus m squared. and then since we're not working with arc length, we have to divide by speed and multiply by the magnitude of dt dt to get the curvature, and when I do that, we get that the curvature is r over r squared plus m squared. Now, so this is for the helix, right? Think about what happens if we put, let's see here, if as r goes to 0, we're going to get the curvature goes to 0, because if you think about r going to 0, you can think about the helix kind of like stretching out into a line. So in some limiting sense, a line has 0 curvature. Technically speaking, lines are not quite covered by the TNB thing, because if you start thinking about it, you can't really define a normal in a unique way for a line, right? If you have the unit tangent, then where's the normal go? Which side of the line, you know? So it's funny, but this stuff we're doing right now really only works best for curves that are more complicated than lines. Lines are too simple for this stuff. Anyway, on the other hand, as m goes to 0, what happens? Basically the helix squashes into a circle, and we get back to our previous result, which is curvature is 1 over r, because a helix with 0 slope is a circle, essentially. On the other hand, we can calculate the unit normal is minus cosine sine, minus sine, and then we can calculate the binormal. Here it is. It's kind of a little bit of a calculation there. It works out to, you know, that. And as a quick check, you can see that b dot n and b dot t are in fact 0. All right. So, and that comes because, you know, either because these are like matching with pluses and minuses, or in the case of the b dot t, it happens because you get a minus sine squared, a minus cosine squared, and so you basically get plus or minus mr from the xy versus the z when you take the dot product. In any event, there's your binormal, and you can differentiate that and take the dot product with n to figure out what the torsion is. Remember, we have to do minus 1 over v because we're working with time parameterization. So minus 1 over the speed, there's my n, there's my b prime, and when you work out that dot product, you'll get m over r squared plus m squared. So the torsion of a helix is m over r squared plus m squared. And it's fun to notice that as m goes to 0, the torsion goes to 0, which makes sense because as m goes to 0, the helix squashes to a circle, which is a planar curve which has 0 torsion. On the other hand, if you think about fixing m and letting r go to 0, you'll get that torsion goes to 1 over m, and that also in a certain sense makes, well, I have not a lot of intuition for the second line, but there it is. So I have foolishly attempted to try to visualize this a little bit more. Students always at some point ask, well, how do you see what you're doing? Like, what does this mean visually? And so I'm still struggling with this, guys. Like, here's an attempt for a two-dimensional visualization. So if we've got this curve, right, and it's a plane curve in the gray, right, that means that the binormal's like the same binormal works for everything. So the Frenese normal points towards the center of curvature in each case, and the tangent points in the direction the curve is going, all right, which I guess I could add in here. Come on, marker. So I'm supposing the curve is like going this direction, right? So that's the one direction the curve is going. Oh, I'm sorry, I try not to bring one direction to anything. But where'd my marker go? Oh, anyway. So on the other hand, this part, I let the curve lift up off the plane. At that point, the purple part of the curve and the transition into the purple part of the curve, right, where it's lifting, there the torsion's non-zero. And this Frenese equation says that the change in the binormal is going to be in the minus direction of the normal at that point. So like the binormal lifts up into the negative normal direction. That's the change in the binormal. And I've been trying to picture that and trying to picture it, and I don't know, here's my next attempt at it. I don't know, it's not, I need a better toy, but you can try to visualize the change in t, the change in n, the change in b in terms of the Frenese equations. And I think I was successful here. If we look at t naught and then like t plus a little bit time later, it should be t naught plus the change in t. But remember, the change in t is basically given by the speed times the curvature times the normal vector times delta t. And so if you look at the direction the tangent changes, it changes into the normal direction, right? Like it's bending into the normal direction. That's what's happening. You can look at it. And I can even see that in the case of a plane curve, the normal direction is also bending into minus the tangent direction in the same way, because the torsion 0. So like this term isn't present. This term isn't present for the plane curve. To understand the change in the binormal, it should be pulling it when the torsion is non-zero. The binormal should be like evolving into the minus normal direction. And so here was my foolish attempt at doing that. I wanted the curve to lift up off the plane, and so when it does that, the normal, of course, is going to be pointing that direction. The original t cross n is pointing into the page, so the binormal points into the page, and then so it should be like pulling that binormal like this way. And apparently by the time it gets over here, it must have like pulled it out. It must have like rotated the binormal all the way up and over. And I think you can actually see that kind of twisting if you look at the animations. I have a GIF on my or GIF. Who cares? That shows the TNB frame. Let me show you. Anyway, my point to you is if you can't visualize it directly, I wouldn't feel bad. It's hard to visualize directly. I should draw your attention. This example in the notes is kind of like a helix, but a little bit different. Here's one example I have, which is not a helix and not a circle. Maybe that's good to look at. I actually do go calculate the curvature and the torsion for that one. Also, I said you could visualize curvature a little bit, and so here it is essentially. If you look at the point with the tangent, and then a little bit later, and then the tangent's evolved, you can look at the angle between before and after and call that the what's that called? I think it's the angle of inclination, maybe, or I forget what this angle's called, but let me call it phi. And the rate of change of that angle is with respect to arc length is actually, or rather the arc length change in arc length with respect to that angle is plus or minus the curvature. So that's one way you can understand curvature, and you can understand it in terms of the rate of change of the angle between the tangent vector and the tangent vector a little bit further along. And here's an explicit example why the larger the curvature is, the faster you change the angle. Like here, I have a unit tangent and a unit tangent and a particular arc length. As you can see, the angle between this and that doesn't change too much. On the other hand, here's the same arc length, but for a much larger curvature. And as you can see, when we subtend that arc length, the direction of the tangent before and after is completely altered. So, in short, larger curvature changes the tangent vector direction much faster, given the same, arc length. Actually, calculating the equations for the oscillating circle is kind of tough. I describe how to do it here. I don't think I actually have an explicit example in the notes. Sorry about that. But here's the picture I was talking about. If you can find the GIF of this, I'll see if I can. You can actually kind of see the binomial kind of whipping around as the curve evolves. This particular curve is actually like take a donut and wrap a string around a donut. That's where that curve's coming from. So it's just like wrapping a string around a donut. I think this is the one my brother said that if you actually calculate the explicit formula for the curvature in a computer algebra system, the formula for the curvature was like 10-page long, and the formula for the torsion is something like 50 pages. So it's not hard to come up with relatively uncomplicated curves which have really, really horrible formulas for curvature and torsion. So I have to be very careful what I assign students in terms of actual explicit examples. It almost necessarily falls back to a helix for me. But anyway, I would finally like just to share with you that this is the first chapter in an ongoing story in mathematics where the program of our investigation was to try to understand the shape of curves by attaching, this tangent, normal, and binormal. And just to tell you, like, the punchline here is, in high school, you might have asked the question, like, I don't know, when is this curve, you think of my watch as a curve, when is this curve and this curve congruent, right? Like, when is it the same shape but in a different place? Maybe this and the other one's like this, or this one's here, but this one's like this way, or this way, or this way. How do you decide when you have the same shape in a different spot? And curvature and torsion give an answer to that. They say that if you have two curves and you can calculate their curvature function and their torsion function, and those functions match up, that means that those are actually the same curve. They've just been moved and rotated. Curves which share the same curvature and torsion are congruent in the sense of high school geometry. So once you understand that, it's a very exciting result. I think it's exciting. You can disagree. And then that next natural question is like, okay, great. So what if you have two surfaces? Like one's here and another one's here. How do I decide whether this surface and this surface are actually the same surface, just in different spots, right? How can we describe the shape of a surface? And so that leads to the investigation of Darboux and so forth, ultimately leading to the work of Cartan on exterior differential systems. And this is still ongoing, and it's actually led to a revolution in the theoretical understanding of differential equations, which persists till this day. I think it's very interesting. Anyway, this is just a window into that world, and in terms of your responsibilities, pretty much you just need to be able to take a curve and calculate T, N, B, curvature and torsion. There, by the way, are all kinds of special formulas for curvature and torsion. I don't expect you to know any of those, really. If you can work through the problems like I show in the notes here, you should be fine. And as always, if you can work the homework, you're doing well. So anyway, I hope that made sense, and I'll stop here. Thanks.